I want to spend some time with you on something that came up when I was working on making a Vieta's formula, you know, the Vieta's results. And it was dealing with polynomials with complex coefficients. And so I have this quadratic here with complex coefficients. You can see that the x term has a complex number coefficient of 3 plus 3i. And then this constant term here is minus 4 plus 12i. And I know you can use the quadratic formula, but when I did it, you know, you get the square root of a complex number, which takes some time to deal with. And so I wanted to just experiment with factoring the thing. And I found out that, and maybe this is something that's well known to everybody, but let me show you what I discovered here. And it's something that was new to me. There's a lot of things like that. But you remember, like, say, for example, you have something like this, say x squared plus 7x plus 12. And you want to factor it, right? Okay. Well, it's well known that all you have to do is find two numbers whose sum is 7 and whose product is 12. And the two numbers that meet that criterion are 3 and 4, right? So done. And that's easy enough when you're dealing with just natural numbers, or, you know, real numbers, I guess. But again, the criterion here, and again, I'm repeating something that everybody knows, but you used the same idea on this, which was kind of interesting. Again, 3 times 4 is 12, and 3 plus 4 is 7, right? 7 and 12. Well, so the same thing came up here, which was interesting to me. So we've recopied the problem right here, and I just wrote this down because it's a little more housekeeping going on, but we're looking for a pair of factors here such that these constants x sub 1 and x sub 2 will sum up to 3 plus 3i, which is the coefficient of x, just like 7's the coefficient of x over here, right? 7's the coefficient of x, and 4 plus 3 is equal to 7. 12 is the constant term, 3 times 4 is equal to 12. We're doing exactly the same thing here. We're assuming if there's a factorization, you're going to have a sum that's equal to, you're going to have a sum that's equal to this coefficient of x, and you're going to have a product that's equal to this constant term. And this whole, this entire thing right here would be behaving like your constant term, right? So you guys can see what happened here. What I did is I wrote it down. I said, oh, that should be x sub 2, folks. That's a mistake. That's x sub 2 right there. Okay, x sub 1 times x sub 2. But notice that you can factor this thing into minus 4 times 1 minus 3i. Just like over here, 12 is equal to 3 times 4, right? And so sure enough, we end up with 3 and 4 as, you know, related to the factorization here. Well, the very same sort of thing happens right here. Remember the rational zero theorem for integer valued polynomials? Well, it looks like something similar that happens for these complexes, because minus 4 and 1 minus 3i are definitely divisors, if you want to call them that, or factors of this. And you can see right over here, if you add 4 plus minus 1 plus 3i, you get 3 plus 3i, which is exactly what we wanted right here, right? And then if you multiply, you get minus 4 plus 12i, which is the constant term. Isn't that cool? All right. So that tells us that this original expression that we were trying to factor factors exactly like this: x plus 4, right? X plus 4 times x plus minus a 1 plus 3i. Just exactly like this, except we're just dealing with complex numbers. Now, it's a little more convenient to write this like this, because then we get it in that well-known x, and I'll write it like this, folks: x minus a negative 4. I like doing it this way, all right? Because remember, the form is x minus r1, x minus r2, and so on. And so right here, this would be x minus your complex 0 right here. Well, I'm just recopying it, but you know what I'm, okay. 1 minus 3i. Now what that tells us is that these guys are also the zeros, right? Remember, there's a correspondence between factors and zeros. So the solution set for the original problem is actually just going to be -4. It's kind of fun to go back in and verify. It's not too hard to verify that -4 gives you a 0 right here, but it's a little more time consuming to verify that 1 minus 3i. Okay. But again, we used, I guess, a version of it. I never had heard of it, but we used a version of the rational zero theorem here. We were just dealing with complex numbers. We used the rational zero. And it's not, they're not really rational in that sense, but they are divisors, okay? They are divisors, and that's exactly what you do. There's a coefficient of 1 right here, so technically everything's divisible by 1, but we're talking about the rational zero theorem as it applies to complex numbers. So anyway, I thought it was kind of neat. It came in handy for me. All right, y'all. Hope you enjoyed.